Welcome back to Cosmic Sedation, your peaceful haven for a night of deep relaxation. Tonight, we explore the enigmatic question: why is Earth the one and only habitable planet? As you drift off with us, don't forget to subscribe and like if you enjoy these calming journeys. Drop a comment letting us know where you are from tonight and what time you usually fall asleep. And so begins our tranquil night together. May it be restful and rejuvenating. Amidst the cosmic silence, Earth's restless crust dances to a geologic rhythm, rewriting borders every geological heartbeat. Beneath our feet, the tectonic plates shift at an average pace of just a few centimeters each year. Yet this constant motion has sculpted entire continents over billions of years. The Eurasian plate, for example, moves roughly 25 millimeters per year towards the north-northeast. This slow dance is imperceptible to us, but profoundly reshapes our planet's surface. Consider a single human lifetime. In just 80 years, land masses can drift hundreds of kilometers, altering coastlines and climates. While this might seem inconsequential on a daily basis, it underpins Earth's dynamic environment, continuously renewing its soils and creating new habitats. The movement of these plates is not uniform. They slide past each other along fault lines like the San Andreas Fault in California, where the Pacific Plate grinds horizontally against the North American Plate. This lateral motion averages about 3 centimeters per year, equivalent to the thickness of a credit card over a decade. Yet this minute shift can trigger significant seismic activity when energy is suddenly released during an earthquake. The 1906 San Francisco earthquake was caused by a sudden displacement along this fault line, releasing decades' worth of built-up tension in just seconds. This event not only devastated the city, but also highlighted the relentless power of plate tectonics beneath our feet. At the center of this activity lies the Mid-Atlantic Ridge, an underwater mountain range where new oceanic crust is born. Here, magma wells up from beneath the Earth's mantle, solidifying into basalt and pushing apart the North American and Eurasian plates. This process occurs at a rate of approximately 2 to 5 centimeters per year. Were you to witness this event from a submarine, you would see hot liquid rock cooling rapidly into jagged cliffs, a spectacle that repeats itself tirelessly across millions of years. In contrast, when plates collide, as with the Indian and Eurasian plates, they create mountain ranges like the Himalayas. This collision has been ongoing for approximately 50 million years, giving rise to the highest peaks on Earth. The force exerted by this convergence averages around 4 centimeters of crustal shortening per year, equivalent to a layer of paper folding over itself once every 2 months. For perspective, imagine standing at base camp as Everest grows taller each year, an incremental but relentless process that underscores Earth's enduring transformation. This slow accumulation has not only created the highest peaks on our planet, but also sculpted vast mountain ranges like the Andes and the Alps. These mountains are more than just breathtaking landscapes. They play a vital role in shaping regional climates by influencing wind patterns and precipitation. For instance, the Himalayas act as a climatic barrier that channels monsoon winds over South Asia, providing crucial water resources to billions of people. The tectonic plate's ceaseless motion is driven by the heat from our planet's core and mantle, which radiates outwards like a slow-burning candle. This geothermal energy keeps the plates fluid enough to slide past one another. However, this internal warmth also has an ancient origin. It was inherited from Earth's formation 4.54 billion years ago, when a Mars-sized body collided with our young planet, distributing heat across its layers. This event not only created our moon, but also set the stage for life's emergence on Earth by regulating temperature and atmosphere stability. The constant reshaping of continents by plate tectonics plays a crucial role in maintaining Earth's habitability. For instance, it contributes to the recycling of nutrients through volcanic activity, enriching soil and promoting biodiversity. Additionally, the movement helps regulate atmospheric CO2 levels over geological timescales. Without this process, we would not have the stable conditions necessary for complex life forms to thrive. The plate tectonic cycle ensures that our planet remains a hospitable environment, constantly evolving while maintaining the delicate balance required for life. Each shift, each collision, each new crust formation is part of an intricate dance that has been unfolding since Earth's birth, shaping the very landscapes we call home. This dynamic system not only supports life, but also influences global climate patterns and ocean currents, further emphasizing how plate movements are integral to Earth's unique ability to sustain diverse ecosystems over billions of years. The Earth's orbit around the Sun is neither perfectly circular nor perfectly stable. It oscillates in a complex dance that could easily push our planet too close to or too far from the life-sustaining warmth of its star. Yet, over billions of years, Earth has maintained an average distance of about 150 million kilometers, a delicate balance known as the Goldilocks zone. This position ensures that the surface temperature remains a comfortable 15 degrees Celsius on average, allowing liquid water to persist and nurture life. Imagine if Earth were just slightly closer or farther away. Oceans would boil or freeze, rendering life impossible. The human body is finely tuned for this narrow window of conditions. Too much heat and proteins denature. Too little and cells cease to function properly. The moon plays a crucial role in stabilizing Earth's axial tilt at approximately 23.5 degrees. This tilt ensures the moderate seasonal changes we experience, preventing either half of our planet from becoming perpetually frozen or scorching hot. Without this stability, life as we know it could not have evolved. Remarkably, the moon is slowly drifting away from Earth at a rate of about 3.8 centimeters per year. In billions of years, it will no longer be able to exert its stabilizing influence on our axial tilt. This gradual drift underscores how finely tuned each element of our planetary system must be for life to flourish. The moon's gentle pull not only influences tides, but also subtly affects the length of a day on Earth. Over time, this tidal braking effect has slowed Earth's rotation by an average of about 1.8 milliseconds per century. Earth's orbit stability is further maintained through gravitational interactions with other planets and celestial bodies in our solar system. These interactions create resonances that help stabilize Earth's path around the Sun. For instance, Jupiter's massive gravity acts as a shield, deflecting potential threats like asteroids and comets away from Earth. This protective mechanism has been crucial for maintaining the Goldilocks orbit over billions of years. The gravitational influence of other planets also causes slight variations in Earth's orbital eccentricity, which can lead to changes in climate patterns, but do not significantly alter our planet's overall habitability. The Sun, which appears constant from Earth's perspective, is actually an active star with a complex magnetic field and internal dynamics that could potentially disrupt planetary stability over long timescales. Solar flares, coronal mass ejections, and changes in solar radiation can all influence the habitability of planets. However, Earth's position within its orbit means it receives a steady amount of energy, about 174 petawatts of continuous solar power. This consistent input fuels our planet's climate systems, driving weather patterns and maintaining ecosystems that have evolved to harness this predictable source of light and heat. If the Sun were slightly more active or less, so the balance of life on Earth would be tipped precariously towards extinction or stagnation. Earth's magnetic field, generated by the dynamo effect within its liquid outer core, acts as a shield against harmful cosmic radiation. This protection is crucial for maintaining life's delicate chemical balances. The field strength varies across the globe, but it generally measures around 30 to 60 microteslas at Earth's surface, enough to deflect most charged particles from space. If this magnetic field were to weaken significantly, as it has done in the past during geomagnetic reversals, the increased radiation exposure could damage DNA and lead to higher rates of mutations in living organisms. The current strength of our magnetic field is finely tuned to protect life at Earth's surface, while also allowing for just enough cosmic rays to seed cloud formation and influence weather patterns. In contrast to the relatively stable Goldilocks orbit of Earth, many exoplanets discovered by astronomers exhibit highly elliptical orbits that would render them inhospitable. These extreme variations in distance from their stars cause dramatic shifts in temperature, ranging from scalding hot days to freezing cold nights that are incompatible with life as we know it. The stability of Earth's orbit is a rare and precious phenomenon, one that has allowed for the development of complex ecosystems over billions of years. Despite the potential for disruption by cosmic events or gradual changes within our solar system, Earth continues to occupy its vital position, a testament not just to its own resilience, but also to the intricate balance maintained across the entire cosmos. The Earth's atmosphere began as a thick blanket of methane and carbon dioxide, dense enough to obscure even the earliest forms of light from reaching its surface. This primordial soup was not conducive to the complex chemistry that would later support life. However, within just hundreds of millions of years, microorganisms emerged, beginning an invisible war for survival that would transform the planet's atmosphere. These tiny organisms, known as cyanobacteria, produced oxygen as a waste product from photosynthesis, a process that remains fundamental to Earth's current biosphere. While early atmospheric oxygen levels were negligible, less than 0.1% compared to today's 21%, the increase during the Great Oxygenation Event, around 2.4 billion years ago, was significant enough to trigger a series of chemical reactions that would support eukaryotic cells. This shift allowed for the development of mitochondria, cellular powerhouses capable of using oxygen to produce energy through aerobic respiration. The rise in oxygen also led to an increase in ozone levels, forming a protective layer in the upper atmosphere that shielded early life from harmful ultraviolet radiation, an unexpected benefit that would have otherwise hindered the evolution of complex organisms. As oxygen levels increased, so too did its reactivity, leading to dramatic shifts in the composition and chemistry of the Earth's surface. Iron-rich rocks, exposed at the Earth's surface, began to oxidize, turning red as they reacted with atmospheric oxygen. This process is responsible for the rust-red coloration visible on many ancient rock formations today, a marker of an atmosphere that was once far different from our own. The oxidation of iron not only changed the landscape, but also influenced cloud formation and reflective properties, playing a role in regulating Earth's temperature, a feedback loop that helped maintain climate stability. The transformation of Earth's atmosphere into its current state took place over billions of years, yet it is one of the most significant factors contributing to our ability to exist on this planet. Without the oxygen produced through photosynthesis, neither complex cells nor the vast diversity of life forms we see today could have evolved. The iron in your blood, for example, was not always as abundant or accessible. Its availability increased significantly after the Great Oxygenation Event, enabling more efficient respiration and energy production in organisms. This shift underscored a paradox. While oxygen is essential for most life on Earth, it was initially toxic to early anaerobic bacteria that dominated the planet. The evolution of Earth's atmosphere also played a pivotal role in shaping its magnetic field, a phenomenon that shields us from harmful cosmic radiation and solar winds. As the molten iron core cooled and solidified into layers, convection currents generated an electromagnetic field around the planet. This process, known as the geodynamo, not only provided protection, but also influenced the composition of the atmosphere by trapping certain gases and allowing others to escape into space. The magnetic field thus contributed indirectly to the atmospheric changes that made Earth habitable for life forms like us. Today, our atmosphere is a balance of gases evolved through interactions between life and its environment. This dynamic system continues to change subtly as new species emerge or existing ones adapt. For instance, recent human activity has altered this equilibrium by increasing atmospheric CO2 concentrations at rates unprecedented in Earth's geological history. While we often focus on the visible impacts of climate change, it is important to remember that such shifts are part of a much larger, ongoing process, millions of years in the making and millions more yet to unfold, each step bringing us closer to understanding how this planet became uniquely suited for life as we know it. Volcanic activity on Earth is not just a spectacle of nature. It is a vital process that continually recycles our planet's crust. Each eruption releases gases and minerals from deep within the Earth, enriching the surface with new materials necessary for life. The average volcanic island grows at an incremental rate of about 1 centimeter per year, yet this slow accumulation over millennia builds entire mountain ranges. Consider the immense pressure building beneath these volcanoes. As tectonic plates collide or diverge, they create fissures that allow molten rock to rise and break through the surface. This process reshapes Earth's crust, ensuring it remains dynamic rather than static. The heat released during an eruption can reach temperatures exceeding 1200 degrees Celsius, enough to melt most rocks on the planet. At any moment, there are approximately 1,500 active volcanoes on land and undersea, contributing to what geologists call plate tectonics. These eruptions release vast amounts of heat, equivalent to the energy used by millions of homes in a single year. This constant thermal output helps regulate Earth's internal temperature, much like a thermostat. Volcanic activity is also crucial for the long-term stability of our magnetic field. The churning liquid iron and nickel within the outer core generate electric currents that sustain our protective shield against cosmic radiation. Without this recycling process, Earth might lose its magnetism entirely, exposing life to harmful solar winds. Yet, despite these monumental forces, the impact on human daily experience is often subtle and gradual. Ironically, while volcanic activity can devastate local ecosystems when it erupts, over geological timescales, it nurtures life by redistributing nutrients across the planet. For instance, the ash from a single eruption can cover thousands of square kilometers, enriching soils and fostering new growth that supports diverse biological communities. This cyclical process has been ongoing for billions of years, shaping Earth's surface and enabling life to flourish. Volcanic activity also plays a role in climate regulation. The release of carbon dioxide during eruptions contributes to the greenhouse effect, helping maintain Earth's average temperature at 15 degrees Celsius, ideal for liquid water. Without this balance, our planet might become too cold or too hot for life as we know it. This delicate equilibrium has been maintained over billions of years, allowing complex organisms like us to thrive. In addition, volcanic islands like Hawaii are prime examples of this ongoing geological activity. These islands emerge from the ocean as lava cools and solidifies atop seafloor spreading centers. The Hawaiian archipelago stretches over 2,400 kilometers, with each island representing a snapshot in time, a testament to millions of years of molten rock extruding onto Earth's surface. This continuous creation showcases how volcanic processes build not just mountains, but entire landscapes. Volcanic activity also influences ocean chemistry by releasing carbon dioxide into the sea. This gas dissolves in seawater and reacts with minerals, altering pH levels and affecting marine ecosystems. These chemical changes have occurred for billions of years, shaping the evolution of life in oceans and contributing to the complex web of biological interactions on our planet. Understanding these processes helps us appreciate not only how volcanoes shape Earth's surface, but also its intricate underwater world. Finally, it is worth noting that despite the destructive power of eruptions, they are essential for maintaining Earth's habitability. By continually recycling its crust and enriching soil with nutrients, volcanoes support life across the globe. They ensure that our planet remains a dynamic and hospitable environment, uniquely capable of sustaining complex organisms like us. This process has been ongoing since Earth's formation 4.5 billion years ago, and will likely continue for billions more. Volcanic activity on Earth is not just a spectacle of nature. It is a vital process that continually recycles our planet's crust. Each eruption releases gases and minerals from deep within the Earth, enriching the surface with new materials necessary for life. The average volcanic island grows at an incremental rate of about 1 centimeter per year, yet this slow accumulation over millennia builds entire mountain ranges. Consider the immense pressure building beneath these volcanoes. As tectonic plates collide or diverge, they create fissures that allow molten rock to rise and break through the surface. This process reshapes Earth's crust, ensuring it remains dynamic rather than static. The heat released during an eruption can reach temperatures exceeding 1200 degrees Celsius, enough to melt most rocks on the planet. At any moment, there are approximately 1,500 active volcanoes on land and undersea, contributing to what geologists call plate tectonics. These eruptions release vast amounts of heat, equivalent to the energy used by millions of homes in a single year. This constant thermal output helps regulate Earth's internal temperature, much like a thermostat. Volcanic activity is also crucial for the long-term stability of our magnetic field. The churning liquid iron and nickel within the outer core generate electric currents that sustain our protective shield against cosmic radiation. Without this recycling process, Earth might lose its magnetism entirely, exposing life to harmful solar winds. Yet, despite these monumental forces, their impact on human daily experience is often subtle and gradual. Ironically, while volcanic activity can devastate local ecosystems when it erupts over geological timescales, it nurtures life by redistributing nutrients across the planet. For instance, the ash from at a depth of nearly 4,000 kilometers beneath the surface, Earth's core is an environment where metals are compressed into states unparalleled anywhere else in the solar system. The pressure here reaches over 3 million atmospheres, enough to crush diamonds into dust. This extreme compression causes iron and nickel to behave like viscous fluids, their atoms squeezed so tightly together that they can barely move. At temperatures hovering around 6,000 degrees Celsius, hotter than the surface of the sun, the core remains remarkably stable despite being at the center of our dynamic planet. The dynamo effect within this molten metal sea generates Earth's magnetic field, a vital shield against harmful cosmic radiation. This electromagnetic bubble deflects charged particles from the solar wind, protecting life on the surface. The stability and strength of this field have been safeguarding Earth for over 4 billion years. Interestingly, if you were somehow able to withstand the heat and pressure, you would be floating in what is essentially an ocean of metal, not unlike how fish navigate through water. However, the core's magnetic field also exhibits unexpected fluctuations that could potentially disrupt global navigation systems and satellite communications. The core's intense pressure creates unique forms of matter not seen elsewhere in the solar system. Some scientists theorize that under these extreme conditions, metals could form supionic states, where ions float freely within a dense electron sea. This peculiar state might even contribute to the generation of Earth's magnetic field. The pressure at the core is so great it defies common understanding, creating an environment where time itself seems to slow down as atoms are compressed beyond recognition. At depth exceeding 3,000 kilometers, the compression rate approaches 1 nanosecond per second, significantly altering atomic interactions and potentially influencing the dynamo effect. The relentless compression in the core not only sustains our magnetic field, but also helps regulate the flow of heat from the interior to the exterior, influencing global climate patterns. This immense pressure could crush a mountain into dust in an instant, yet it quietly supports conditions necessary for life to exist on Earth's surface. The stability and unique properties of this environment are essential for the delicate balance that allows life to thrive. Moreover, these extreme pressures might even influence geological processes like plate tectonics, which contribute to the recycling of nutrients critical for life. This paradoxical environment, hostile yet vital, is what makes ERRTH Chinese letter, 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 Chinese letter. Earth's core's intense pressure not only shapes metallic alloys into unique states, but also fuels our planet's magnetic field. Without this constant churning and compression, life as we know it might never have had the shield it needs to survive harmful cosmic radiation. At a depth of nearly 4,000 kilometers beneath the surface, Earth's core is an environment where metals are compressed into states unparalleled anywhere else in the solar system. The pressure here reaches over 3 million atmospheres, enough to crush diamonds into dust. This extreme compression causes iron and nickel to behave like viscous fluids, their atoms squeezed so tightly together that they can barely move. At temperatures hovering around 6,000 degrees Celsius, hotter than the surface of the sun, the core remains remarkably stable despite being at the center of our dynamic planet. The dynamo effect within this molten metal sea generates Earth's magnetic field, a vital shield against harmful cosmic radiation. This electromagnetic bubble deflects charged particles from the solar wind, protecting life on the surface. The stability and strength of this field have been safeguarding Earth for over 4 billion years. Interestingly, if you were somehow able to withstand the heat and pressure, you would be floating in what is essentially an ocean of metal, not unlike how fish navigate through water. This magnetic cocoon ensures that charged particles do not interfere with Earth's atmosphere and its delicate balance. The dynamo effect within the core generates this protective electromagnetic field by constantly churning and compressing metals under immense pressure. This process also influences global climate patterns, maintaining stable conditions necessary for life to flourish on the surface. The stability of this field is crucial for sustaining ecosystems that depend on a consistent environment. The core's intense pressure creates unique forms of matter not seen elsewhere in the solar system. Some scientists theorize that under these extreme conditions, metals could form supionic states, where ions float freely within a dense electron sea. This peculiar state might even contribute to the generation of Earth's magnetic field. The pressure at the core is so great it defies common understanding, creating an environment where time itself seems to slow down as atoms are compressed beyond recognition. The relentless compression in the core not only sustains our magnetic field, but also helps regulate the flow of heat from the interior to the exterior, influencing global climate patterns. This immense pressure could crush a mountain into dust in an instant, yet it quietly supports conditions necessary for life to exist on Earth's surface. The stability and unique properties of this environment are essential for the delicate balance that allows life to thrive. Moreover, these extreme pressures might even influence geological processes like plate tectonics, which contribute to the recycling of nutrients critical for life. This paradoxical environment, hostile yet vital, is what makes ERRTH Chinese letter, 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 Chinese letter. Earth's core's intense pressure not only shapes metallic alloys into unique states, but also fuels our planet's magnetic field. Without this constant churning and compression, life as we know it might never have had the shield it needs to survive harmful cosmic radiation. Earth's magnetic field is a dynamic force, constantly shifting and adjusting like the heartbeat of our planet. This invisible shield extends far beyond our atmosphere, reaching into space where it interacts with solar winds and cosmic radiation. The magnetosphere, as this protective bubble is known, stretches to about 10 times Earth's diameter, safeguarding all life on its surface. Each cell in your body benefits from this magnetic field by deflecting high-energy particles that could otherwise damage DNA. Without this barrier, harmful radiation would bombard the planet's surface, making it impossible for complex organisms to thrive. The strength of our magnetic field fluctuates over time, sometimes weakening and leaving us more vulnerable to cosmic threats. This dynamic nature is crucial for maintaining a stable environment conducive to life. The dynamo effect within Earth's liquid outer core generates this protective shield through the churning of molten iron and nickel. These metals flow in complex patterns, creating electric currents that produce magnetic fields. The heat from Earth's solid inner core fuels these movements, driving convection currents essential for sustaining the magnetosphere. This process is so powerful it can influence compass needles on the surface. However, an unexpected fact about this dynamo effect is that it occasionally produces multiple poles instead of just two, creating temporary magnetic anomalies across different regions of the globe. The strength of Earth's magnetic field is measured in nanoteslas, a unit that might seem insignificant at first glance. For context, our planet's current magnetic field measures around 30 to 65 microteslas near the surface. To put this into perspective, a typical refrigerator magnet has a strength of about 100 micro-T. Despite their small scale, these measurements are crucial for deflecting particles with energies up to several gigaelectronvolts. While most people remain unaware of this constant protection, the magnetosphere plays a vital role in shaping our environment. It not only shields us from harmful radiation, but also influences space weather and satellite communications. The interaction between solar winds and Earth's magnetic field creates fascinating phenomena like auroras near the poles when charged particles collide with atmospheric gases. These displays of light, known as the northern and southern lights, offer a glimpse into the dynamic interplay between our planet's magnetic shield and its outer space environment. While these lights may seem distant from Earth's surface, they are direct evidence of the invisible forces at work above us. Magnetic field reversals mark significant periods in Earth's history when poles flip, creating times when the protective shield weakens. These events occur approximately every few 100,000 years, but are rarely a cause for concern over human timescales. The last full reversal happened around 13.8 thousand years ago, and while it might seem like a long time, geological processes work on much larger timeframes than our daily lives. Despite this, the continuous activity of Earth's magnetic field ensures that life continues to thrive in relative safety. These reversals can also cause temporary disruptions in navigation systems and satellite communications, highlighting the delicate balance maintained by this invisible shield. The magnetosphere also plays a crucial role in moderating climate by deflecting high-energy particles that would otherwise heat up our atmosphere excessively. This regulation is vital for maintaining stable temperatures across Earth's surface, contributing to the conditions necessary for life to flourish. The magnetosphere's influence on climate stability underscores its importance not just as a protective barrier, but also as an environmental regulator. The interaction between solar winds and Earth's magnetic field creates fascinating phenomena like auroras near the poles when charged particles collide with atmospheric gases. These displays of light, known as the northern and southern lights, offer a glimpse into the dynamic interplay between our planet's magnetic shield and its outer space environment. While these lights may seem distant from Earth's surface, they are direct evidence of the invisible forces at work above us. Earth's magnetic field is not only crucial for life on the surface, but also plays a role in shaping the solar system around it. The magnetosphere interacts with the solar wind, creating a boundary known as the magnetopause where these two forces meet. This interaction can cause temporary disruptions in satellite communications and navigation systems, highlighting the delicate balance maintained by this invisible shield. Earth's magnetic field is not only crucial for life on the surface, but also plays a role in shaping the solar system around it. The magnetosphere interacts with the solar wind, creating a boundary known as the magnetopause where these two forces meet. This interaction can cause temporary disruptions in satellite communications and navigation systems, highlighting the delicate balance maintained by this invisible shield. Earth's magnetic field is not only crucial for life on the surface, but also plays a role in shaping the solar system around it. The magnetosphere interacts with the solar wind, creating a boundary known as the magnetopause, where these two forces meet. This interaction can cause temporary disruptions in satellite communications and navigation systems, highlighting the delicate balance maintained by this invisible shield. Earth's magnetic field is not only crucial for life on the surface, but also plays a role in shaping the solar system around it. The magnetosphere interacts with the solar wind, creating a boundary known as the magnetopause, where these two forces meet. This interaction can cause temporary disruptions in satellite communications and navigation systems, highlighting the delicate balance maintained by this invisible shield. Earth's magnetic field is not only crucial for life on the surface, but also plays a role in shaping the solar system around it. The magnetosphere interacts with the solar wind, creating a boundary known as the magnetopause, where these two forces meet. This interaction can cause temporary disruptions in satellite communications and navigation systems, highlighting the delicate balance maintained by this invisible shield. Earth's magnetic field is not only crucial for life on the surface, but also plays a role in shaping the solar system around it. The magnetosphere interacts with the solar wind, creating a boundary known as the magnetopause, where these two forces meet. This water's journey across our solar system reveals a stark contrast between its liquid state on Earth and its vapor or ice states elsewhere. On Venus, the average surface temperature hovers around 465 degrees Celsius, hot enough to melt lead. This extreme heat forces water into a perpetual gaseous state, making it impossible for life, as we know it, to exist on this scorching planet. In stark contrast, Earth's average surface temperature remains at approximately 15 degrees Celsius, ideal for liquid water to persist. This delicate balance is maintained by our planet's position within the solar system, about 150 million kilometers from the Sun, just right for nurturing life. The proximity of Earth to its star provides a stable environment where water can maintain its liquid form without evaporating into vapor or freezing solid. Mars presents another extreme case in the state of its water resources. With average temperatures around -63 degrees Celsius, Mars is far too cold for liquid water to exist on the surface. Here, water exists primarily as ice, locked away beneath layers of dust and rock. This icy terrain underscores how Earth's unique axial tilt of about 23.5 degrees helps maintain stable seasons and climate patterns, crucial for sustaining life. Earth's magnetic field further contributes to its ability to sustain liquid water by shielding it from harmful cosmic radiation. Venus lacks a significant magnetic field, leaving its atmosphere vulnerable to solar winds and charged particles that strip away lighter gases like hydrogen and helium into space. This loss of atmospheric mass over billions of years has contributed to the extreme conditions on Venus. The Moon's stabilizing influence on Earth extends beyond just maintaining axial tilt. It also helps regulate tidal forces that influence oceanic currents. These currents play a crucial role in distributing heat around the planet, further ensuring stable conditions conducive to liquid water and life. This intricate web of planetary interactions highlights how interconnected our solar system truly is. Earth's position within the Goldilocks zone, neither too close nor too far from the Sun, ensures that it maintains its vital liquid water resources. The planet orbits at an average distance of 150 million kilometers, receiving just enough sunlight to keep temperatures in a range suitable for life. This balance has allowed Earth to support diverse ecosystems over billions of years, while other planets have either frozen or boiled away their potential habitats. Water's journey across the solar system reveals stark contrasts between its liquid state on Earth and its vapor form on Venus or ice on Mars. On Venus, surface pressures reach nearly 90 million pascals, squeezing water molecules into vapor. This intense pressure and heat create an atmosphere so dense that any trace of water is quickly evaporated. Meanwhile, Mars offers a glimpse into what happens when conditions are too cold for sustained liquid water. The Martian polar ice caps contain vast reserves of frozen carbon dioxide, as well as water ice, locked away beneath the thin atmosphere. These icy regions represent a stark contrast to Earth's abundant liquid water resources, illustrating how crucial temperature regulation is for maintaining life-supporting environments. Earth's unique combination of atmospheric pressure and greenhouse gases plays a pivotal role in sustaining its precious liquid water. The delicate balance maintained by carbon dioxide, methane, and other trace gases keeps the planet warm enough to prevent water from freezing entirely. This interplay between different atmospheric components underscores how finely tuned our environment is for supporting life. The Moon's stabilizing influence on Earth extends beyond just maintaining axial tilt. It also helps regulate tidal forces that influence oceanic currents. These currents play a crucial role in distributing heat around the planet, further ensuring stable conditions conducive to liquid water and life. This intricate web of planetary interactions highlights how interconnected our solar system truly is. Earth's magnetic field not only protects against cosmic radiation, but also influences climate patterns through its effect on weather systems. The charged particles deflected by this invisible shield can influence cloud formation and precipitation cycles, which in turn affect the distribution of water across the globe. This multifaceted role underscores how essential Earth's magnetic field is for sustaining life-friendly conditions. Earth's position within the Goldilocks zone, neither too close nor too far from the Sun, ensures that it maintains its vital liquid water resources. The planet orbits at an average distance of 150 million kilometers, receiving just enough sunlight to keep temperatures in a range suitable for life. In contrast, Venus is located much closer to the Sun, with surface temperatures reaching around 465 degrees Celsius. This proximity drives water into vapor form, creating dense clouds that contribute to its runaway greenhouse effect. The intense heat and pressure on Venus render it inhospitable to liquid water, let alone complex life forms. Mars, positioned farther from the Sun, experiences average surface temperatures of about -63 degrees Celsius. Water on Mars exists primarily as ice due to the planet's thin atmosphere and low pressures. This icy terrain underscores how Earth's unique position in the solar system is key to sustaining its liquid water resources, a crucial factor for life. The Moon's stabilizing influence on Earth's axial tilt helps maintain consistent seasons and climate patterns, essential for sustaining liquid water. By gently tugging at Earth's axis, the Moon ensures that our planet maintains a stable 23.5-degree tilt, preventing extreme climate variations. This stability is critical for maintaining the conditions necessary to support life. Earth's magnetic field further contributes to its ability to sustain liquid. Standing at a tectonic plate boundary feels like standing on ground that's subtly shifting, yet it's more than just imperceptible movement. It's a reminder of Earth's dynamic nature. While most people wouldn't notice anything unusual, geologists can measure this drift with precision, just 13.2 centimeters each year. This slow motion is akin to watching the hands of a clock tick. It's so gradual that you might miss the significance unless you pause to consider it. Yet, these minute shifts have shaped entire mountain ranges over millennia, transforming landscapes from seas into continents. The Himalayas, for instance, are still rising by less than a centimeter annually due to this relentless movement. Imagine pressing your hand against a pane of glass, smooth and unyielding in the moment, yet capable of shattering under enough force. For example, when two plates grind past each other with immense pressure, they can create friction that heats up to temperatures as high as several hundred degrees Celsius at depth. This heat builds over years until it's released suddenly during earthquakes, sudden ruptures in the Earth's crust where energy stored from compression is unleashed. The San Andreas Fault in California exemplifies this, a line where two plates meet and slide past each other at an average rate of 5 centimeters per year, with occasional bursts of seismic activity that can reshape the landscape dramatically. The heat generated from plate movement is remarkable but often overlooked. As these massive slabs collide or grind against one another, they create friction that heats up to temperatures as high as several hundred degrees Celsius at depth. This thermal energy contributes to volcanic eruptions and geothermal activity, phenomena that are both dangerous and essential for life's sustenance on Earth. The heat also plays a crucial role in the formation of hydrothermal vents, which support unique ecosystems teeming with microbial life far beneath the ocean floor. These environments reveal how even extreme conditions can nurture life forms adapted to thrive in such inhospitable settings. To grasp the scale of these movements, consider that Earth's plates have been shifting for nearly 4.5 billion years, a time period so vast it defies human comprehension. While each plate moves at a rate similar to fingernail growth, this continuous motion has rearranged continents and oceans over eons. The Pacific plate alone is one of the largest, covering more than half the Earth's surface area beneath the ocean. Its relentless movement contributes to the creation of new seafloor as it spreads apart along mid-ocean ridges. This process not only reshapes the planet's surface, but also plays a critical role in regulating global climate patterns by influencing ocean currents and carbon cycling. The boundary between two tectonic plates is more than just a line on a map. It's a dynamic frontier where geologic forces collide. At these points, rocks deform through folding and faulting, creating intricate geological structures. These processes often lead to the formation of mountains like the Andes or the Alps, which are products of plate collision over millions of years. The pressure involved in such collisions can also metamorphose rocks, transforming them into denser, more compact forms under immense heat and stress. This transformation is a testament to the power of geological forces that operate on timescales far beyond human perception. Understanding these movements reveals how Earth's surface is not static, but an ever-changing mosaic. Each plate carries unique features, oceans, mountains, and plains that are shaped by its interactions with neighboring plates. The Pacific Plate, for example, subducts beneath other plates at places like the Mariana Trench, the deepest point in any ocean. Here, one plate slides under another, descending into the Earth's mantle where it melts and becomes part of the cycle that regenerates the planet's crust. This constant recycling ensures that our world remains geologically active, capable of sustaining diverse ecosystems for billions more years to come. In a billion years, Earth's sun will have grown hotter and more luminous, radiating 40% more energy than it does today. This increased output is due to the sun's core hydrogen reserves dwindling, causing nuclear fusion reactions to accelerate and the star to expand into its red giant phase. As a result, Earth will receive significantly more radiation, pushing temperatures beyond the threshold for sustaining liquid water. As the sun's temperature rises, it will trigger a series of changes in Earth's atmosphere. Water vapor, a potent greenhouse gas, will increase dramatically due to higher temperatures, trapping even more heat and accelerating this warming trend. This positive feedback loop could lead to dramatic shifts in climate patterns, potentially disrupting ecosystems that have evolved over billions of years. The increased solar radiation will cause changes in Earth's orbit and rotation, leading to significant variations in the planet's climate zones. These changes could disrupt ecosystems that have evolved over billions of years, forcing species into new survival strategies or extinction. While some organisms may adapt to these new conditions, many others will not be able to cope with such dramatic environmental shifts. The Moon has played a crucial role in stabilizing Earth's axial tilt at about 23.5 degrees, preventing extreme climate variations and maintaining stable seasons. However, as the sun grows brighter, this stability could be compromised. The increased solar radiation will cause changes in Earth's orbit and rotation, potentially leading to significant shifts in the planet's climate patterns. These changes could disrupt ecosystems that have evolved over billions of years, forcing species into new survival strategies or extinction. While some organisms may adapt to these new conditions, many others will not be able to cope with such dramatic environmental shifts. The Moon's influence on Earth has been a constant for life as we know it, but in this future scenario, its stabilizing effect might become less pronounced. In the distant past, Earth's surface temperature was far cooler than it is today. When our planet formed around 4.5 billion years ago, Conditions were harsh and hostile to complex life forms. The early Earth was bombarded by meteorites and experienced intense volcanic activity that created a thick atmosphere rich in carbon dioxide. Despite these challenges, the formation of liquid water and the development of stable climates allowed for the emergence of simple life forms. These organisms thrived in environments far different from those we see today. Over time, through processes such as plate tectonics and atmospheric evolution, Earth became more hospitable to diverse life. The transition from a young, volatile planet to one capable of supporting complex ecosystems is a testament to the resilience and adaptability of both our planet and its inhabitants. The core of Earth plays a vital role in maintaining the conditions necessary for life. At a depth of nearly 4,000 kilometers beneath the surface, Earth's core generates a magnetic field that shields us from harmful cosmic radiation. This invisible force extends far beyond our atmosphere, reaching into space where it interacts with solar winds and cosmic radiation. As the sun grows brighter, this protective shield may weaken, exposing Earth to increased levels of radiation. The weakening of the magnetic field could lead to higher rates of cosmic particle bombardment, potentially affecting life on the surface. This scenario highlights the delicate balance between our planet's internal dynamics and its ability to support life. As we contemplate this distant future, it's important to recognize that Earth has always been in a state of constant change. From the formation of its core billions of years ago to the ongoing evolution of life, our planet has continually adapted to new conditions. In a billion years, when the sun's increasing luminosity renders Earth uninhabitable for current life forms, we may be left with only memories of this vibrant, dynamic world. Yet, the legacy of Earth's habitability will live on in the stars and planets that bear witness to its once thriving ecosystems. The story of our planet is a profound reminder of the delicate balance between stellar evolution and planetary survival, a balance that has been central to life's development over billions of years. Earth's axial tilt is stabilized by the Moon at approximately 23.5 degrees relative to its orbital plane around the Sun. This consistent angle ensures that seasons change predictably and provides stable environmental conditions necessary for complex life to thrive. The gravitational pull of the Moon acts like a gyroscope, maintaining Earth's axis within a narrow range that allows for consistent seasonal cycles. This stabilization is crucial because any significant variation in axial tilt could lead to extreme climate shifts, rendering vast portions of Earth uninhabitable. For instance, if our tilt were to vary widely over time, it would result in erratic seasonal changes, disrupting agricultural cycles and threatening the survival of countless species. The Moon's gravitational influence helps prevent such fluctuations, ensuring a stable environment conducive to life. The Moon's stabilizing effect not only maintains consistent seasons, but also plays a role in slowing Earth's rotation over geological timescales. As it does so, days on Earth have lengthened from just under 6 hours to the current 24-hour cycle. This slower rotation is important for moderating temperature fluctuations and further supporting life's ability to adapt. It allows for more balanced heat distribution across the planet, which is crucial for the development of diverse ecosystems. Interestingly, this stabilizing effect of the moon is not unique in the universe, but is rare among terrestrial planets within our solar system. Venus, for example, lacks a significant moon and experiences extreme climate variations due to its slow rotation period of about 243 Earth days. This inconsistency in seasonal patterns makes it inhospitable for complex life forms. The presence of the moon has allowed Earth's climate to develop in a way that supports diverse ecosystems. Furthermore, this stability provided by the moon has allowed Earth's climate to develop in a way that supports diverse forms of life. The consistent seasons have enabled the development of various ecosystems, from tropical rainforests to polar ice caps. This environmental consistency is particularly important for species like humans who rely on predictable seasonal patterns for agriculture and migration. Without this stabilizing influence, the world we know would be vastly different, potentially devoid of the complex life that thrives here today. The moon's gravitational interaction with Earth not only maintains a stable axial tilt, but also influences ocean tides, which play a critical role in marine ecosystems. The regular tidal cycles help distribute nutrients and support diverse aquatic life forms. This interplay between celestial bodies underscores how interconnected different aspects of our planet are. It is fascinating to consider that the very presence of the moon has such profound effects on Earth's biological systems. In addition, the moon's stabilizing effect has implications for the long-term future of Earth. As the sun continues its life cycle and expands into a red giant phase in about 5 billion years, the stable climate provided by the moon will be crucial for maintaining habitable conditions as long as possible. This stability is not just beneficial for current life forms, but also offers hope that certain ecosystems might persist even under changing stellar conditions. It is a reminder of how small nuances in our solar system's architecture can have far-reaching consequences for the future of life on Earth. Understanding the moon's role in stabilizing Earth's axial tilt provides insight into the intricate web of conditions that make our planet habitable. This delicate balance highlights how finely tuned each element must be for a planet to support life over billions of years. The moon's influence extends beyond just stabilizing the axial tilt. It also contributes to the overall stability of Earth's rotation and orbit, creating an environment where complex life can flourish. Clouds are not just transient formations in the sky. They are dynamic systems involving trillions of water molecules at any given moment. Each molecule moves within a complex dance governed by temperature and pressure gradients. This intricate process begins with evaporation from Earth's vast bodies of water, including oceans, lakes, and rivers. As these water molecules rise into cooler air layers, they condense around tiny particles like dust or salt, forming droplets that eventually coalesce into clouds. The average surface temperature on Earth, approximately 15 degrees Celsius, is ideal for sustaining this cycle of evaporation and condensation. This precise balance allows liquid water to exist in abundance, a rarity in our solar system. On Mars, for instance, the thin atmosphere means that any water present exists primarily as ice or vapor. Clouds play an indispensable role in regulating Earth's temperature by reflecting sunlight back into space, while also trapping heat near the surface through greenhouse gases like water vapor. This balance is crucial for sustaining life on our planet, which relies heavily on stable temperatures to support diverse ecosystems and human civilization alike. Each cloud formation helps maintain this equilibrium, contributing to a global climate that remains hospitable for all forms of life. Interestingly, high-altitude clouds tend to trap heat near the Earth's surface, while low-level clouds can reflect sunlight away from Earth, cooling the planet. This complex interaction between different types of clouds demonstrates how finely tuned our atmosphere is for sustaining life. Clouds also influence the climate by acting as both coolers and warmers, depending on their altitude and composition. High-altitude cirrus clouds tend to trap heat near the Earth's surface, contributing to warming effects. In contrast, low-level stratus or cumulus clouds can reflect sunlight away from Earth, cooling the planet by an average of 10 watts per square meter. This complex interaction between different types of clouds demonstrates how finely tuned our atmosphere is for sustaining life. Clouds are not just passive actors in this cycle. They actively shape the environment around them. When large masses of warm air rise and cool, they create towering cumulonimbus clouds, often associated with thunderstorms. Each cloud formation contributes not just to weather patterns, but also to the overall water cycle on Earth. The process starts with evaporation, where water from oceans, lakes, and rivers turns into vapor and rises. As this vapor cools in the upper atmosphere, it condenses into tiny droplets or ice crystals. These accumulate over time, forming clouds that eventually release precipitation back onto the surface. This continuous loop is vital for sustaining life on Earth, ensuring a steady supply of fresh water to ecosystems across the globe. Clouds are more than just fleeting spectacles in the sky. They are integral parts of Earth's climate system. Their formation and behavior reflect the intricate balance between temperature, humidity, and air pressure, conditions unique to our planet. This delicate equilibrium has allowed life to thrive for billions of years, making clouds a vital component in maintaining Earth's habitable environment. For instance, without this balance, Earth could experience extreme variations in climate that would make it inhospitable for most forms of life. Clouds are dynamic entities that change constantly as they move across the sky. They form, grow, dissipate, and reform throughout their life cycle, all within minutes or hours. This ever-changing nature makes clouds fascinating subjects for observation, revealing much about our atmosphere's complex dynamics. For example, when a cloud system moves over land, it can alter local weather patterns by either bringing precipitation or blocking out sunlight, thus influencing temperature and humidity levels in the area. Consider a single raindrop falling from a cloud. It is small, barely noticeable against the vastness of the sky. Each droplet contains about 1/10 of a milliliter of water, enough to fill just a tiny section of your fingertip. Yet, in the context of Earth's oceans, this drop pales into insignificance. The world's oceans encompass an area so immense that if you were to pour all the raindrops from every cloud on Earth simultaneously, it would not even make a noticeable dent. The Pacific Ocean alone covers nearly 67 million square kilometers, holding more than half of the planet's total water volume. This vast expanse is crucial for regulating global climate and supporting diverse ecosystems. In contrast to a mere raindrop, the oceanic currents play an intricate role in distributing heat across the globe, helping to moderate temperatures and ensure habitable conditions on our planet. The movement of these currents can be as slow as several centimeters per second, but has profound effects on weather patterns that shape life around the world. Imagine now a single raindrop falling into one of Earth's oceans. It merges with trillions more like it, each contributing to the global water cycle that sustains life. The ocean is not just a collection of vast expanses. It is a living system that interacts with the atmosphere, land, and even the deep interior of our planet. This interconnectedness underscores how delicate Earth's balance is for sustaining life. A single raindrop might seem insignificant, yet every drop contributes to the complex web that supports all life forms on this unique blue planet. Earth's oceans are not only vast in area, but also in depth. The average depth of the ocean floor is about 3 kilometers below sea level, with some areas plunging over 10 times deeper than Mount Everest rises high above sea level. At these depths, pressures reach hundreds of atmospheres, far beyond what most creatures could endure on land. Yet, within this extreme environment, life thrives in various forms, from bioluminescent fish to microbes that metabolize minerals at hydrothermal vents. The contrast between the shallow raindrop and the deep-sea ecosystems reveals the remarkable adaptability of life under vastly different conditions. The stability of Earth's climate, which allows for liquid water to exist on its surface, is a result of numerous factors working in harmony. Among these are the greenhouse gases that trap heat from the sun, keeping the planet warm enough for water to remain liquid. The average surface temperature of 15 degrees Celsius is ideal for sustaining life as we know it. This delicate equilibrium contrasts starkly with Mars, where temperatures can drop below -63 degrees Celsius, and Venus, where they soar past 450 degrees Celsius. The temperature range on Earth allows raindrops to fall as liquid water rather than vapor or ice, highlighting how our planet's specific position relative to the Sun is critical for life. While a single raindrop might be fleeting and ephemeral, it reflects the profound complexity of Earth's systems. Each drop contributes to the global hydrological cycle, which governs weather patterns, supports ecosystems, and shapes landscapes over time. The contrast between this minuscule droplet and the vastness of our oceans underscores how interconnected everything on Earth truly is. In this intricate balance, life finds its place amidst a universe where conditions suitable for liquid water are exceedingly rare. In the vacuum of space, temperatures plummet far below anything we experience on Earth's surface. The human body, accustomed to an average temperature range between 16 and 22 degrees Celsius, would struggle to register such extreme cold if exposed directly. Spacecraft must maintain internal temperatures above 0 degrees Celsius to prevent equipment from freezing. Yet this is a mere fraction of the true frigid depth awaiting outside. At an altitude of about 100 kilometers from Earth's surface, where the International Space Station orbits, the temperature can drop to -84 degrees Celsius or lower. This might seem cold enough to freeze any exposed skin instantly, but our senses deceive us here. The lack of air to conduct heat means that while temperatures are indeed extremely low, they do not directly affect the human body unless direct contact is made with a freezing surface. It's paradoxical. On Earth, we experience cold through conduction and convection, yet in space, these very mechanisms are absent. Imagine standing on a platform floating just above the atmosphere, unprotected from the void beyond. The sensation would be akin to stepping into a freezer set at its coldest setting, but with one critical difference: you feel nothing. This is because cold is essentially the absence of heat, and in the vacuum of space, there's no medium like air or water to transfer that absence directly onto your skin. The human body relies on sensors such as nerve endings to detect changes in temperature, but without a thermal gradient from an environment to our bodies, those signals don't trigger the familiar shivers we associate with cold. The vacuum of space also amplifies another sensory limitation. Sound cannot travel through it because there are no molecules to carry vibrations. Silence envelops you, not just as the absence of sound, but in its most absolute form, the complete lack of any medium for sound waves to exist. This silence is so profound that if you were to shout, your voice would never reach another human ear. It's a reminder of how isolated we are from one another when beyond Earth's protective atmosphere. However, this isolation can be interrupted by the occasional crackling noise known as space static, generated by solar winds interacting with the spacecraft or spacesuit materials. Despite the absence of direct thermal sensation, prolonged exposure to space's extreme cold can lead to severe physiological changes. At -84 degrees Celsius, tissues and bodily fluids begin to lose their liquid state. The water in your blood, tears, saliva, essentially all moisture within you, would start to vaporize into space due to the low pressure. This process is so rapid that it could potentially lead to a condition known as ebullism, the formation of gas bubbles inside body tissues and fluids. Spacecraft are equipped with life support systems designed to maintain internal temperatures well above freezing, ensuring astronauts remain comfortable and protected from the biting cold of space. These systems work by generating heat through electrical resistance or other means, highlighting how technology must compensate for the harsh realities outside Earth's warm embrace. Yet, it is a constant reminder of our reliance on artificial environments to survive in the vastness beyond. Magnetic field reversals are not just isolated events. They often occur in clusters known as geomagnetic excursions. During these periods, the magnetic poles become highly unstable, sometimes even reversing multiple times before settling into a new configuration. The Lachamp event, which took place around 41,000 years ago, is one such example where the Earth's magnetic field weakened dramatically for nearly 2 millennia. These geomagnetic excursions have been linked to significant environmental changes, including shifts in global weather patterns and increased cosmic radiation exposure. For instance, during the Lachamp event, some regions experienced prolonged periods of cold climate conditions, which could have influenced early human migrations out of Africa. The correlation between magnetic field fluctuations and climatic shifts highlights the intricate relationship between Earth's geodynamics and its habitability. Moreover, these events provide valuable information for paleoclimatologists studying past climates. By analyzing sediment cores and ice samples from different epochs, scientists can reconstruct ancient environmental conditions and better understand how global systems respond to such dramatic changes. This knowledge helps us anticipate potential future scenarios as we continue to monitor Earth's magnetic field and its effects on our planet's ecosystems. Understanding the frequency of these reversals is crucial for predicting their impact on future life forms. Currently, researchers estimate that a full reversal occurs roughly every 250,000 years, with variations in intensity and duration. The most recent complete reversal happened approximately 780,000 years ago during the Matayama-Brunnes boundary. While these reversals are inevitable geological events, their effects on life can vary significantly depending on the rate of change and overall environmental conditions at the time. For example, a rapid reversal could lead to more severe disruptions compared to a gradual one, potentially causing widespread ecological shifts. Scientists continue to study these phenomena to better understand how Earth's magnetic field influences living organisms over long timescales. In contrast, some species have shown remarkable resilience during past reversals. The fossil record reveals that certain marine creatures, such as foraminifera and calcareous nanoplankton, experienced significant changes in their shell structures, coinciding with geomagnetic excursions. These adaptations suggest an evolutionary response to altered environmental conditions, indicating the dynamic nature of life's adaptation strategies. By examining fossil records, scientists have identified several periods in Earth's history when magnetic field reversals coincided with significant extinction events. One such instance is the end Permian mass extinction approximately 251 million years ago, which wiped out nearly 96% of marine species and 70% of terrestrial vertebrates. During these reversal periods, increased cosmic radiation penetration could have damaged DNA in organisms, leading to higher mutation rates or even death. Additionally, changes in climate patterns and ocean circulation might have exacerbated environmental stressors, contributing to the loss of biodiversity seen in fossil records. These findings highlight the interconnectedness between geological events and biological evolution. Interestingly, some researchers propose that magnetic field reversals could also influence plate tectonics. The weakening of Earth's magnetic shield during these periods may allow more cosmic radiation to penetrate through the atmosphere, potentially affecting atmospheric pressure gradients. and thus influencing mantle convection patterns beneath the crust. This connection suggests a broader interplay between geophysical processes on different scales. The impact of geomagnetic excursions extends beyond immediate environmental changes. They also leave lasting imprints in Earth's geological record. Scientists can detect these events through variations in magnetic minerals embedded within rocks, known as paleomagnetism. These records provide a timeline of past field reversals and help refine our understanding of the geodynamo process responsible for generating Earth's protective shield. Paleomagnetic studies have revealed that some periods of intense geomagnetic activity coincide with significant evolutionary transitions in life forms. For example, the Triassic-Jurassic boundary marks both a major extinction event and an increase in geomagnetic field instability. This temporal overlap suggests that magnetic field reversals may contribute to environmental stresses that drive speciation events. In the future, as Earth continues its journey around the Sun, it will likely experience more geomagnetic excursions. These events remind us of the dynamic nature of our planet and the resilience of life in adapting to changing conditions. 20 million years ago, hominin-like creatures began to walk upright on Earth, marking a pivotal moment in our planet's evolutionary history. Their posture allowed for better visibility and more efficient movement across varied terrains. These early bipedal walkers were part of an intricate web of environmental factors that supported their survival and evolution. The Earth's magnetic field, already well established by this time, provided crucial protection from harmful cosmic radiation. The magnetic shield generated within the planet's liquid outer core had been safeguarding life for billions of years. This invisible barrier extended far beyond our atmosphere, interacting with solar winds and cosmic radiation to protect early hominins as they ventured across the landscape. The strength of this field varied over time, sometimes reversing its polarity in events that could have wiped out nascent life forms if not for their resilience or adaptation. Yet, it's easy to overlook this detail when considering the vastness of space, where unprotected celestial bodies are bombarded by cosmic radiation. The specific conditions of Earth at that time, such as a stable atmospheric composition and moderate temperatures, were critical for the survival of these early hominins. The planet's distance from the Sun ensured that liquid water could exist in abundance, essential for all known life forms. This delicate balance allowed life to flourish and evolve over millions of years. As these bipedal ancestors walked across the plains, they were part of a larger process, the continuous recycling of Earth's crust through volcanic activity. Volcanic eruptions released gases and minerals from deep within the Earth, enriching the surface with nutrients necessary for life. However, some of these eruptions also periodically ejected large amounts of ash into the atmosphere, which could have temporarily cooled global temperatures by blocking sunlight. This unexpected cooling effect created a delicate balance that both challenged and supported early hominin evolution. Each step these creatures took was not just a physical action, but also a profound moment in evolutionary history. They were at the beginning of a journey that would eventually lead to humanity as we know it today. Their upright posture allowed better visibility over tall grasses and more efficient movement across varied terrains, giving them an edge in survival. The Moon played a pivotal role in stabilizing Earth's axial tilt at around 23.5 degrees relative to its orbital plane. This consistent angle ensured that seasons changed predictably, providing stable environmental conditions necessary for the complex life forms that would evolve on Earth. The stabilization of Earth's axial tilt by the Moon is a subtle yet crucial factor in the evolution of life. It's easy to overlook this detail when considering the grand scale of cosmic events. Yet, without this stabilizing influence, climate fluctuations could have been extreme enough, such as temperature swings exceeding 50 degrees Celsius, to prevent the development of complex life forms. The early hominins experienced stable seasons that supported their survival and evolution. These bipedal walkers were just beginning to adapt to Earth's environment, learning to use simple tools and developing social structures. Their cognitive abilities were still evolving, but they were on a path towards higher intelligence. The Moon's gravitational pull not only stabilized the axial tilt, but also influenced ocean tides, which may have played a role in shaping early coastal environments where these hominins could find resources. The interaction between lunar gravity and Earth's waters created rhythmic patterns that could have affected migration routes and food availability for these early bipedal walkers, further supporting their adaptation to the environment. The greenhouse effect on Earth is a finely tuned process that keeps our planet's average surface temperature at about 15 degrees Celsius, allowing liquid water to exist and support life. This balance is maintained by atmospheric gases like carbon dioxide and water vapor, which trap heat from the sun. In contrast, Venus suffers from an extreme greenhouse effect due to its thick atmosphere of carbon dioxide, leading to surface temperatures hot enough to melt lead. On Earth, these gases are present in just the right quantities to maintain a stable climate. Water vapor plays a pivotal role in this balance by absorbing and re-emitting infrared radiation, further warming the planet. This cycle includes evaporation from oceans, condensation into clouds, and precipitation back onto the surface. The distribution of heat across Earth's latitudes is also crucial. Regions near the equator are warmer than those closer to the poles due to variations in solar energy received. This temperature gradient supports diverse ecosystems, from tropical rainforests to Arctic tundras. The stability of Earth's greenhouse effect over geological timescales is remarkable. Silicate rocks on the surface slowly react with carbon dioxide, removing it from the atmosphere and stabilizing temperatures. This process acts as a thermostat for our planet, preventing runaway warming or cooling. In contrast, Mars has lost much of its early atmosphere due to solar winds, leaving it too cold today for liquid water. Human activities have recently altered this delicate balance by increasing atmospheric carbon dioxide levels from 280 parts per million during the pre-industrial era to over 415 ppm in recent years. This rise is primarily driven by deforestation and fossil fuel combustion, leading to global warming, with significant impacts on climate patterns and ecosystems worldwide. The tilt of Earth's axis at about 23.5 degrees relative to its orbital plane around the Sun is another factor that stabilizes our planet's temperature distribution. This axial tilt causes seasons, which moderate climate variations across different latitudes. Without this tilt, parts of the planet would experience extreme heat, while others would be locked in perpetual cold, making life as we know it impossible. The greenhouse effect on Earth is a finely tuned process that keeps our planet's average surface temperature at about 15 degrees Celsius, allowing liquid water to exist and support life. This balance is maintained by atmospheric gases like carbon dioxide and water vapor, which trap heat from the Sun. In contrast, Venus suffers from an extreme greenhouse effect due to its thick atmosphere of carbon dioxide, leading to surface temperatures hot enough to melt lead. On Earth, these gases are present in just the right quantities to maintain a stable climate. Water vapor plays a pivotal role in this balance by absorbing and re-emitting infrared radiation, further warming the planet. This cycle includes evaporation from oceans, condensation into clouds, and precipitation back onto the surface. The distribution of heat across Earth's latitudes is also crucial. Regions near the equator are warmer than those closer to the poles due to variations in solar energy received. Surprisingly, this temperature gradient can cause unexpected weather phenomena such as polar vortexes that bring extremely cold air from the Arctic down into lower latitudes. The stability of Earth's greenhouse effect over geological timescales is remarkable. Silicate rocks on the surface slowly react with carbon dioxide, removing it from the atmosphere and stabilizing temperatures. This process acts as a thermostat for our planet, preventing runaway warming or cooling. In contrast, Mars has lost much of its early atmosphere due to solar winds, leaving it too cold today for liquid water. Human activities have recently altered this delicate balance by increasing atmospheric carbon dioxide levels through deforestation and fossil fuel combustion. These changes are leading to global warming, with significant impacts on climate patterns and ecosystems worldwide. Understanding these processes helps us appreciate the complexity of Earth's systems and the challenges we face in maintaining a stable environment for future generations. The tilt of Earth's axis at about 23.5 degrees relative to its orbital plane around the Sun is another factor that stabilizes our planet's temperature distribution. This axial tilt causes seasons, which moderate climate variations across different latitudes. Without this tilt, parts. At this boundary where Earth's troposphere meets its stratosphere, temperatures drop sharply by about 65 degrees Celsius over just a few kilometers. This transition zone is known as the tropopause and marks one of the most dramatic changes in temperature on our planet. The air pressure also decreases significantly here, making it an inhospitable environment for complex life forms. The tropopause acts like a barrier between two distinct atmospheric realms. Below it, the weather happens. Storms, clouds, and precipitation all occur within the troposphere. Above, the stratosphere is relatively calm, with fewer disturbances. This stability in the upper atmosphere allows for the formation of the ozone layer, which absorbs harmful ultraviolet radiation from the sun. Interestingly, this boundary is not unique to Earth. Other planets like Venus and Mars have similar transitions between their lower and upper atmospheres. However, the specific conditions at Earth's tropopause are finely tuned to support life. The temperature drop here prevents water vapor from rising too high into the atmosphere, which helps maintain a stable climate system. The pressure difference across this boundary is significant. While it might seem abstract, consider how this affects air travel. Commercial airplanes often fly just below the tropopause where the air is denser and offers better lift for fuel efficiency. This thin layer of atmosphere is crucial for aviation and global transportation networks. Despite its critical role in regulating Earth's climate, the tropopause remains a challenging environment for scientific study. Instruments must be designed to withstand extreme conditions, including both temperature fluctuations and pressure changes. Yet, understanding this boundary helps us better predict weather patterns and long-term climate trends. Scientists use advanced remote sensing technologies to gather data from this region. Reflecting on Earth's unique position in the universe, it becomes clear that our planet's habitability is a result of many finely balanced factors. The tropopause, with its sharp temperature gradient, plays a crucial role in maintaining conditions suitable for life. The process by which this boundary forms is both complex and fascinating. As warm air rises from the Earth's surface, it cools until it reaches a point where its temperature matches the surrounding environment at that altitude. This is known as adiabatic cooling. Once this equilibrium is reached, the air stops rising, creating a stable layer above. This mechanism not only explains why weather systems tend to form below the tropopause, but also highlights how Earth's climate is finely tuned by natural processes. The tropopause acts as a ceiling for weather phenomena like storms and clouds, effectively limiting their vertical extent. Below this boundary, water vapor condenses into clouds, leading to precipitation that replenishes freshwater resources on our planet. Above, in the stratosphere, conditions are stable enough for the ozone layer to form, absorbing harmful ultraviolet radiation. This protective shield is vital for life on Earth, as it prevents excessive ultraviolet exposure, which can lead to DNA damage and other health issues. The stability of this boundary also influences global weather patterns. For instance, jet streams, fast-flowing air currents in the upper atmosphere, are confined to the lower stratosphere just above the tropopause. These powerful winds play a crucial role in shaping weather systems across continents, guiding storms and influencing climate variability. Understanding these dynamics helps meteorologists predict severe weather events like hurricanes or monsoons with greater accuracy. The tropopause, therefore, is not merely an atmospheric transition, but a key regulator of Earth's climate system. It ensures that the conditions necessary for life remain stable over time. To experience the Mariana Trench is to confront an environment where human standards of comfort are utterly irrelevant. At nearly 11 kilometers below sea level, the pressure reaches over 1,000 atmospheres, a force that would crush even the most robust submersibles designed for shallower depths. The water here is not merely cold, it is approaching freezing temperatures just above 2 degrees Celsius. This frigid environment contrasts sharply with the warmth of Earth's surface, yet it supports life in ways we are only beginning to understand. These extremophiles, living off chemical energy from hydrothermal vents, thrive where sunlight cannot reach. Descending deeper into this abyss, one encounters a realm where sound travels 5 times faster than it does through air. The dense water acts as an efficient conduit for low-frequency sounds, allowing marine creatures to communicate over vast distances. Infrasound can travel thousands of kilometers here, enabling organisms to navigate and hunt in the darkness. The trench itself is a product of Earth's tectonic processes, shaped by the collision between the Pacific Plate and the Mariana Plate. This ongoing geologic dance has created not only the deepest point on our planet, but also other oceanic trenches scattered around the globe. The pressure at these depths is so intense that it can bend metal like clay, a testament to the relentless forces shaping Earth's surface. Despite its extreme conditions, the Mariana Trench plays a crucial role in regulating global climate and supporting marine biodiversity. Hydrothermal vents on its floor produce minerals and chemicals that feed entire ecosystems, thriving far from sunlight. These organisms have adapted over millions of years to survive in an environment where light is absent, but chemical energy is abundant. In this context, Earth's habitable zones extend beyond the sunlit surface into deep, dark regions where life persists through other means. The Mariana Trench represents a unique laboratory for understanding how extremophiles adapt and thrive in environments that are inhospitable to most forms of life we know. This environment underscores the diversity of habitats on our planet and highlights the resilience of life in the face of extreme conditions. The pressure at such depth is so intense that it can alter the behavior of water itself, making it denser than liquid found near the surface. This density difference plays a critical role in global ocean circulation patterns, driving currents that influence weather systems far above the trench's surface. These deep-sea processes are invisible to most of us, but profoundly shape our world. The organisms living here have evolved unique survival mechanisms. Some bacteria can convert hydrogen sulfide into energy, a process known as chemosynthesis. This contrasts sharply with photosynthesis, which relies on sunlight and is the dominant energy source for life near the surface. These deep-sea ecosystems are entirely self-contained, existing in isolation from the rest of Earth's biosphere. The Mariana Trench is not just an extreme environment, it also holds clues about our planet's past. Sediments at the bottom contain records of ancient climates and geological events. By studying these layers, scientists can reconstruct the history of Earth's climate over millions of years. This sedimentary archive is akin to a time capsule, offering insights into how life has adapted to changing conditions throughout Earth's long history. The temperature in the trench varies slightly depending on depth, but it remains consistently near freezing. At this point, the water pressure is so immense that it would crush any unprotected human body within seconds. Yet, for certain species, these extreme pressures are essential for survival. Fish here have adapted with large, all-filled bladders to counteract the crushing weight of the ocean above. The Mariana Trench also serves as a reminder of Earth's dynamic nature. While we often think of our planet as stable, it is constantly changing. The trench itself is formed by geological processes that are still active today. Its depth continues to increase as tectonic plates collide, and one plate subducts beneath another. This ongoing process highlights the ever-evolving landscape of our planet. Jupiter's immense gravitational field acts as a protective shield for Earth, deflecting and absorbing many of the cosmic debris that would otherwise threaten our planet. Every hour, approximately 60 tons of interplanetary material enter Earth's atmosphere, most smaller than a grain of sand. These particles highlight the constant barrage our planet faces, which is greatly reduced by Jupiter's gravitational influence. Without this protection, the influx could increase dramatically, posing significant risks to life on Earth. The gas giant's gravity well acts like a sieve, capturing larger objects that would otherwise threaten us, ensuring a regulated flow of cosmic debris through its neighborhood. Jupiter's size, over 2.5 times greater than all other planets combined, contributes significantly to its protective function. Its gravitational pull exerts an influence far beyond just deflecting objects. It also stabilizes the orbits of nearby asteroids, preventing them from becoming erratic and potentially dangerous. This stabilization can be compared to how traffic lights regulate vehicle flow at intersections. Jupiter ensures a regulated flow of cosmic debris through its region. The scale of this protection is staggering. Jupiter alone accounts for a significant portion of what keeps Earth habitable in its corner of the solar system. Occasionally, Jupiter flings captured debris back into interstellar space, further reducing potential threats to inner planets. This ongoing process has been crucial in maintaining Earth's stable and life-conducive environment. The consistent protection provided by Jupiter extends beyond just deflecting objects. It also helps regulate the climate by preventing large-scale impacts that could cause global cooling or warming events. These impacts have likely occurred on other celestial bodies, such as the Moon's surface, which bears witness to countless meteorite strikes visible from Earth. The Moon, with its heavily cratered landscape, serves as a stark reminder of what could happen if Jupiter were not there to shield us. Without this giant planet, Earth might be subjected to frequent impacts that could disrupt or even extinguish life as we know it. The presence of Jupiter ensures that our planet remains relatively free from these hazardous encounters, allowing for the development and sustenance of complex ecosystems over billions of years. This protective mechanism underscores the delicate balance required for life to thrive on Earth, a balance maintained by forces both cosmic and intricate. Jupiter's influence extends not only in space, but also through time. The asteroid belt between Mars and Jupiter is thought to be remnants of a planet that failed to form due to Jupiter's gravitational interference. This suggests that Jupiter has played a role in shaping the architecture of our solar system since its formation. Understanding this long-term impact helps us appreciate how the presence of such massive planets can influence planetary systems beyond our own, potentially affecting the habitability of distant worlds. Jupiter's magnetic field, one of the strongest in the solar system, further enhances Earth's protection from cosmic radiation and charged particles. This field extends far into space, creating a magnetosphere that traps and deflects harmful particles before they reach Earth. The interaction between Jupiter's magnetosphere and its moons creates auroras similar to those seen on Earth, though much more intense due to the planet's size and magnetic strength. These phenomena highlight the interconnectedness of our solar system, where distant events can have profound effects closer to home. The scale of Earth's weather systems contrasts sharply with human-sized objects, revealing a world where natural forces dwarf even the largest cities or countries. Consider a hurricane. Its eye can span over 100 kilometers in diameter, larger than many metropolitan areas. This vastness is not just about size, but also about energy. Each storm releases more power than thousands of nuclear bombs. Yet within this immense system, there are moments of eerie calm. The eye, where the pressure drops to levels equivalent to what one might experience at high altitudes. To grasp the scale, imagine standing in the eye of a hurricane. The air is deceptively still, with pressures as low as 870 millibars, similar to an altitude of about 3,000 meters. This pressure difference fuels the storm's destructive winds and precipitation outside the calm core. Such extremes highlight how finely balanced these systems are, requiring precise conditions for their formation and maintenance. Beyond the immediate impact on Earth's surface, hurricanes play a crucial role in redistributing heat across our planet. They draw warmth from tropical oceans and transport it toward cooler regions, influencing global weather patterns. This process is vital for regulating temperatures and maintaining climatic stability over long periods. In contrast to these vast movements of energy, human activities often seem fleeting. Another striking aspect is the rapid life cycle of storms. A hurricane can form in just a few days, but weaken within hours if it encounters cooler ocean waters or drier air conditions. This variability underscores how delicate and dynamic Earth's weather systems are. The suddenness with which these massive forces can emerge and dissipate serves as a reminder of nature's unpredictability. While hurricanes are destructive, they also bring essential benefits. They displace warm water from the surface, allowing cooler waters to rise, thus promoting nutrient-rich upwellings that support marine ecosystems. Additionally, the rain brought by storms replenishes freshwater supplies inland, vital for agriculture and drinking water. This dual nature of weather systems highlights their complex role in sustaining life on Earth. As we observe these immense forces at play, it becomes clear how finely tuned Earth systems are for supporting life. The life cycle of a storm, from birth to death, is an intricate dance of temperature, humidity, and pressure gradients. This delicate balance allows for the existence of diverse ecosystems, including those that thrive in conditions created by such extreme weather events. Understanding these processes deepens our appreciation for the planet's resilience and complexity. The sheer size of a hurricane can be difficult to comprehend fully. A Category 5 storm, with winds exceeding 252 kilometers per hour, spans thousands of square kilometers. To visualize this scale, consider that such a storm could easily cover entire countries like France or Spain in its full fury. Yet, despite their vastness, these storms are tightly controlled by the laws of physics, pressure differentials, and temperature gradients driving them with precision. This control is evident in the way hurricanes follow predictable paths under certain conditions, guided by steering currents high in the atmosphere. These invisible forces direct the storm's movement, sometimes causing it to veer or slow down when encountering land masses or cooler ocean waters. This predictability contrasts sharply with the chaotic appearance of a hurricane on the ground, where winds tear through structures and rain falls at alarming rates. The intensity of these storms is further illustrated by their energy output. A single Category 5 hurricane can release more than 200 trillion watts of power, equivalent to the energy consumption of millions of homes for an entire year. This immense power underscores not only the destructive potential, but also the vital role hurricanes play in redistributing heat across our planet's surface. Understanding these phenomena helps us appreciate both the fragility and resilience of Earth's climate systems. While hurricanes can devastate coastal communities, they are part of a larger cycle that maintains global climatic balance. This intricate dance between destruction and creation is essential for sustaining life on this unique blue planet. Earth's surface temperature hovers around 15 degrees Celsius, a range that allows liquid water to persist and life to flourish. This stability is remarkable given Earth's relatively young age of about 4 billion years compared to other planets in our solar system. Mars and Venus, for instance, are older but have not sustained life as long due to their static environments. The dynamic nature of Earth, its shifting tectonic plates, volcanic activity, and magnetic field has fostered conditions that support life. The Moon plays a crucial role by stabilizing Earth's axial tilt at approximately 23.5 degrees relative to its orbital plane around the Sun. This consistent angle ensures seasons change predictably without extreme variations in temperature. The gravitational interaction between Earth and the Moon keeps this tilt stable, preventing chaotic climate shifts that could otherwise render life impossible. This delicate balance is a testament to how small forces can have profound effects on planetary habitability. Earth's magnetic field, generated by its liquid outer core, acts as a shield against harmful cosmic radiation. The dynamo effect within the core produces this protective barrier, which deflects solar winds and charged particles from reaching Earth's surface. This magnetic field is constantly shifting, with reversals occurring at irregular intervals. These shifts have not disrupted life significantly, highlighting how adaptable our planet's systems are to change. The Sun provides Earth with approximately 174 petawatts of continuous energy, equivalent to 10,000 times the world's total energy consumption. This solar power drives weather patterns and sustains ecosystems through photosynthesis. However, the Sun is not static. It will eventually expand into a red giant phase in about 5 billion years, rendering Earth uninhabitable. Yet, for now, this consistent influx of energy supports life's intricate web on our planet. Water covers roughly 71% of Earth's surface, existing in liquid form due to the planet's specific distance from the Sun. This distance is finely tuned, allowing water to remain stable without freezing or evaporating completely. The presence of liquid water has been crucial for the emergence and evolution of life on Earth. Despite this stability, the oceans are not static. They constantly circulate nutrients and support diverse marine ecosystems. Earth's atmosphere composition, 78% nitrogen, 21% oxygen, and trace amounts of other gases, is uniquely suited to supporting complex life forms. This balance has been maintained through a delicate interplay between biological processes and geological activities. The presence of free oxygen in the atmosphere is particularly noteworthy, as it supports aerobic respiration for most organisms on Earth. Yet this atmospheric composition is not eternal. Over time, changes in solar radiation and volcanic activity could alter these proportions, potentially affecting life's ability to thrive. The Moon plays a crucial role in stabilizing Earth's axial tilt at approximately 23.5 degrees relative to its orbital plane around the Sun. This consistent angle ensures that seasons change predictably and provides stable environmental conditions necessary for complex life to thrive. Without this stabilization, Earth could experience extreme climate variations, leading to inhospitable environments for most forms of life. The Moon's gravitational influence also causes tides, which have played a significant role in shaping coastal ecosystems and influencing the evolution of marine species. This interplay between celestial bodies underscores how seemingly distant phenomena can profoundly impact life on Earth. Earth is younger than many other planets in our solar system, having formed around 4.54 billion years ago. Yet, it has supported life for a remarkably long time, approximately 3.8 billion years after its formation. This dynamic environment, characterized by active plate tectonics and volcanic activity, has contributed to the planet's resilience and adaptability. The constant recycling of Earth's crust through volcanic eruptions enriches the surface with essential minerals and nutrients, fostering conditions conducive to life. In contrast, planets like Mars, which formed around 4.5 billion years ago, have become geologically dormant, lacking the dynamic processes that sustain life on Earth. This paradox highlights how a younger planet can be more hospitable for life due to its ongoing geological activity. The presence of liquid water on Earth is not just a matter of temperature. It also depends on the planet's unique distance from the Sun and its atmospheric composition. Water exists in liquid form between approximately 0 degrees Celsius and 100 degrees Celsius under standard pressure. This narrow range creates a Goldilocks zone, where conditions are neither too hot nor too cold for life to flourish. Earth's position within this zone is crucial, as it allows water to remain stable on the surface, supporting diverse ecosystems. However, this stability is not guaranteed indefinitely. In about 1 billion years, increased solar radiation will push Earth beyond Amidst Earth's continuous day-night cycle, plants undergo a vital process known as photosynthesis, converting sunlight into energy. This cycle ensures that during daylight hours, chlorophyll in leaves absorbs light, initiating chemical reactions. At night, these processes pause, allowing for rest and recovery. The balance between day and night is crucial for plant health and growth, influencing the entire food chain. The Earth's surface temperature averages around 15 degrees Celsius, ideal for liquid water to exist. This temperature range supports diverse ecosystems, from tropical rainforests to Arctic tundras. However, this stability contrasts with the extreme temperatures found in space, where objects can reach -270 degrees Celsius. Such cold is so profound that it challenges our understanding of how matter behaves at such low energy levels. Animal migrations are closely tied to Earth's day-night cycle and seasonal changes. Many species travel vast distances to find food or suitable breeding grounds, often following the sun's path across different latitudes. For example, monarch butterflies migrate over 4,000 kilometers annually from North America to Mexico, synchronizing their journey with daylight hours. This migration ensures they can rest during night and feed during day. Human sleep patterns are deeply influenced by Earth's rotation, aligning with the circadian rhythm. Our bodies adapt to this cycle through hormonal changes, such as the release of melatonin at night. Interestingly, astronauts in space must adjust their schedules to artificial light cycles, disrupting natural rhythms that have evolved over millennia on Earth. The Moon plays a crucial role in stabilizing Earth's axial tilt, preventing extreme climate variations and ensuring consistent seasons. This stability is vital for maintaining ecosystems and supporting life forms. However, the Moon also influences ocean tides, creating rhythmic patterns of water movement along coastlines. These tidal cycles are essential for marine life, affecting everything from fish migration to coral spawning. Beneath our feet, the restless crust continues its geologic dance, shifting at an average pace of just a few centimeters each year. This subtle motion has shaped continents over billions of years, sculpting landscapes and creating diverse habitats. The constant movement of tectonic plates not only reshapes Earth's surface, but also contributes to the dynamic ecosystems we observe today, from mountain ranges to ocean basins. The day-night cycle on Earth is a fundamental driver of photosynthesis in plants and algae. As sunlight bathes leaves or algal cells, chlorophyll captures photons to convert carbon dioxide and water into glucose and oxygen. This process not only fuels plant growth, but also provides the oxygen essential for animal life. On average, about 100 billion tons of carbon are fixed annually through photosynthesis, a rate that has remained relatively constant over geological timescales. Yet, this seemingly stable cycle is highly sensitive to environmental changes, such as shifts in temperature or atmospheric composition, which can disrupt ecosystems and alter the balance of gases in our atmosphere. Plants have evolved intricate mechanisms to optimize their exposure to sunlight. Some species adjust their leaf angles throughout the day to maximize light absorption, while others grow taller to reach higher light levels. This competition for sunlight is a key factor in shaping forest structures and biodiversity. In tropical regions, where sunlight is abundant year-round, trees can grow exceptionally tall, creating layered ecosystems with distinct habitats at different heights. Meanwhile, in temperate zones, deciduous forests shed leaves during winter months when sunlight is scarce, conserving energy until spring. The Earth's rotation also influences weather patterns and ocean currents, which are critical for distributing heat around the globe. As the planet spins on its axis, it creates a Coriolis effect that deflects moving air masses and water flows, leading to complex atmospheric and oceanic circulations. These patterns drive everything from gentle breezes to powerful hurricanes, shaping climates across continents and oceans. The Gulf Stream, for instance, carries warm waters northward along the eastern coast of North America, playing a crucial role in moderating temperatures in regions like Europe. Beneath our feet, the restless crust continues its geologic dance, shifting at an average pace of just a few centimeters each year. This subtle movement is part of a larger cycle that reshapes landscapes over millennia. Mountains erode and rebuild. Amidst the cosmic silence, Earth's restless crust continues its gentle dance beneath our feet, shaping and reshaping the world we know in ways both grand and unseen. As this journey through space and time comes to a close tonight, I want to thank you for joining us on this tranquil voyage. If you enjoyed the ride, don't forget to subscribe and like. Your support means everything. Until next time, sleep well beneath the stars.